In this video, we're going to discuss Stokes' theorem. We'll say that a surface is oriented if it has two sides. So that would be most of the surfaces that we've looked at so far. An example of a surface that's not oriented would be a Möbius strip. So here you have a picture of this Möbius strip. This surface only has one side. It is not oriented. So in talking about Stokes' theorem, we'll just stick with our usual oriented surfaces like cones, paraboloids, etc. that have two sides. Here's the statement of Stokes' theorem. We'll let S be an oriented surface in 3D with positively oriented boundary curve C. Then the line integral around C of f dot t ds is equal to the surface integral over our surface S of the curl of our vector field dotted with n ds. Let's draw a few pictures to clarify some of the aspects of this statement. So first, imagine that we've got a surface. It should be an oriented surface, so it could be something like, maybe it's a paraboloid that's opening downwards. So there's our paraboloid, we'll call that S. And then C is representing the boundary curve of our surface. So let's draw another picture here. So if we think about this paraboloid being cut off at the xy plane, then in that xy plane where that surface is being cut off, we're producing this curve here. So that's what's called our boundary curve. You can think of that as being the edge of your surface or the boundary of your surface. And it's important for Stokes' theorem that this is positively oriented. So positively oriented, you can think of that as meaning counterclockwise when viewed from above. You can also think of it as meaning it keeps the surface on its left as we rotate around our curve. So there's our positively oriented boundary curve. And before we get into the physical interpretation of Stokes' theorem, I think I'll just remind us here what d capital S represents. So that's the element of surface area. Geometrically, that just represents a tiny patch of surface area. So it's a tiny little bit, infinitesimal area on our surface. So let's look at a physical interpretation of Stokes' theorem. We have a vector field coming up in the statement of Stokes' theorem, and for this physical interpretation, I say let's just let F represent a force field. And let's look at the right side of the Stokes' theorem equation. So we've got the surface integral over S of curl of F dotted with n ds. And so we can think of that as an infinite sum. What we're summing, let's look at this expression here. So you could say that's the normal component of the curl. We could say it's the magnitude of curl of F in the direction that's perpendicular to our surface. So we're taking that magnitude and then we're multiplying it by this infinitesimal little piece of our surface area. All right, so when we say magnitude of curl of F in direction perpendicular to S, that's just like saying we're taking the curl of F and we're dotting it with the normal vector to our surface to get that magnitude in the perpendicular direction. And then that's being multiplied by ds. So when we look at this sum, this is an infinite sum over infinitely many tiny areas ds. So we'd be breaking our surface up into infinitely many infinitesimal little areas, ds, and for each of those multiplying ds times this magnitude. Now let's think about what this sum here should look like based on just thinking about the physics of what's happening. So we've got this surface, let's say it's a paraboloid, and we've got this vector field that's acting in space. So let's say in the neighborhood of, let's say this point here, this is the force. So if we look at points around here, let's say we look at this point and that point, see there are going to be micro rotations that are induced because of the action of the force. So around this point, you might have a micro rotation. I'll draw it in blue. Micro rotation that looks like that. And around this point here, you might have a micro rotation that looks like that due to the action of our force. So now let's go back to this idea of the magnitude of the curl of our vector field in the direction perpendicular to S. Well, if you look at the curl of F in the direction perpendicular to S, that's speaking to the rotation that's happening on the surface of S. So that magnitude would be incorporating both the amount of rotation that we've got and also the direction of the rotation. So when we start to look at this sum, we're going to get things like some positive number times ds, and then plus some negative number times ds. So I'm not going to worry too much about the exact coefficients here because that would come down to the details of what exactly our vector field looks like at every point. But the idea is that the signs are going to alternate. So you're going to have some positive number times ds minus some negative number times ds, and then you're just going to have this infinite sum where your signs are alternating and your coefficients are varying. So I think just to get at the physical interpretation, I'm okay with just leaving these coefficients unknown. Or we could even say C1 ds minus C2 ds plus C3 ds minus C4 ds, and just mention that all these coefficients here are, let's say, non-negative. So just to focus in on the signs a little bit more, remember that due to the right-hand rule, if you've got a rotation going in this direction, then our curl of F is going to be coming up like that. Whereas if we've got a rotation in the opposite direction, like this, then our curl of F is going to be going in the opposite direction. And so these plus or minus signs are just representing whether curl of F is actually going in the same direction as our normal vector or in exactly the opposite direction. That will vary depending whether we've got the counterclockwise rotation or clockwise rotation on our surface. So we get this alternating sum, and the point is that there's lots of cancellation. So lots of cancellation in the interior of S, and what that leaves us with is a net effect on the boundary of S, which is our curve C. So here's our surface S, and then our curve C in this picture would just be that curve going like that. Okay, so then to think about what the net effect on this curve C would be, well, let's just think about units. So on the right-hand side, let's scroll up to Stokes' equation for a second. On the right-hand side here, what we're integrating is curl of F dotted with NDS. So let's just think units there, and that will tell us what our net effect on C should be. So our units for F, we've said F is a force field, so it's going to be in newtons. Curl of F, well, you're taking partial derivatives with respect to x, y, and z of your vector field, so that's going to be newtons per meter. The unit vector, n, little n, is unitless, so we won't write that down here. And then d capital S meter squared. So on the right side of Stokes' equation, we were taking basically the units of curl of F times the units of ds. So let's just say right side of Stokes' equation, Newton meters. So that tells us what this net effect on C is. It's work. So it's the work done by our vector field, F, on C. Okay, and then what's another way of writing that? Well, we could say it's the line integral around C, because C is a closed curve. You can write a circle on there. And then one way of describing work, vector field F dotted with vector T d little s. So that gives us Stokes' equation. So that's the physical interpretation behind Stokes' theorem, basically saying the work done by F around this closed curve C, well, we're doing the surface integral of the normal component of the curl of F, where this vector n here just representing a unit normal vector to our surface. So let's try to make a connection with something that we saw earlier in the video series. So I've rewritten the Stokes' theorem equation. And let's imagine what would happen if we tried to apply this just in 2D. So let's suppose that our surface S, and therefore its boundary curve C, are in the xy plane. And we'll draw a picture here to help imagine that. So we're in 3D space, but for whatever reason, we're looking at a special surface that's just sitting in that xy plane. So for example, our boundary curve C could be this curve here, and the surface could be just this sort of distorted disc shape that's sitting within that xy plane. Okay, so because S is not a closed surface, when we think about this unit normal vector here, the convention is that we would choose the upper direction for a surface that's not closed. So our upper unit normal vector, little n, would look like 0, 0, 1. So it'd just be going straight up 1 unit in the z direction at every point on our surface. Okay, so let's see what that would mean for Stokes' theorem then. So imagine what would happen if we took the curl of f and we dotted it with this vector n. Then we would just be picking up the z component of the curl, and if we flash back to curl, the z component would look like delta q by delta x minus delta p by delta y, where p and q are components of our vector field. So if we simplify this, we just get delta q by delta x minus delta p by delta y. All right, so I think that's going to give us enough information now to write down basically what Stokes' theorem would look like if we just reduced it to the xy plane. So let's call this 2D version of Stokes' theorem, and I won't give this a name just yet, but let's try to figure out what it would look like. So looking up here, we're going to translate everything into its 2D version. So on the left side, we would have work done around C. So f dot t ds is one way to write that, but another way to write that is just to say p dx plus q dy. And if we are reducing this just to the situation in the xy plane, then we would not have a dz term on here. So we'll just leave it like that. And then we're going to say that's going to be the double integral. Okay, we could say over our surface, but because this is a region of the xy plane, we could also just say double integral over r. And then we've decided that curl of f dotted with n would look like delta q by delta x minus delta p by delta y. Okay, and then because we're integrating over a region of the xy plane, we would write dA here for our dy dx. So this is something we've seen before. This is Green's theorem. So what we're saying is that Green's theorem is a 2D version of Stokes' theorem. So just as a summary of what we've talked about in this video series so far, we've got 4 theorems that I would classify as being important related to vector fields. 2 of them are about work done around a curve, and 2 of them are about flux. So the 2 that are about work are Green's theorem and Stokes' theorem. And then in terms of flux, we've seen the 2D divergence theorem and also the 3D divergence theorem. So in learning these new theorems, I think the more connections you can make between them, the easier it is to remember the formulas and to understand the context in which we're using these theorems.